Today in class we looked at rules 3 and 4, and we are going to use our knowledge from last class to help us figure out what these rules are. So for 3a, we are cubing something. In this case, we're cubing x squared. So that would be x squared times x squared times x squared. And then remember last time, you guys figured out that if we're multiplying the same base, we're going to keep the base the same, and then we can add our exponents. So 2 plus 2 plus 2 is 6. So x squared raised to the third power would be x to the 6th. If it helps you, you could think about writing it out the long way, right? X squared would be x times x squared is x times x, times another x squared, which is x times x, and then you can see we really are multiplying x by itself 6 times. B is similar, so this time we're going to square x to the 4th. We're going to multiply it by itself twice. Again, from last time, you guys figured out when we're multiplying the same base, we keep our base the same, and we add our exponents. So 4 plus 4 is 8. So we get x to the 8th. Again, if it helped you to think about it the long way, x to the 4th would be x times x times x times x times another x to the 4th, x times x times x times x, and then you can see we really are multiplying x by itself 8 times. C is a little different because there's a coefficient inside the parentheses. There's that 2 in front of the x to the 4th. But if we still think about it through the same lens that we did with A and B, right, we're cubing something. What is it that we're cubing? In this case, we're cubing 2x to the 4th. That means we need to take 2x to the 4th and multiply it by itself 3 times. So 2x to the 4th times 2x to the 4th times 2x to the 4th. And then just like last class, when we were multiplying things, we rearranged them so we could think about that as 2 times 2 times 2. Times x to the 4th times x to the 4th times x to the 4th. And I'm going to rewrite that to help us really think about what's happening here. So we have 2 times 2 times 2. I'm going to rewrite that as 2 cubed. And then we have x to the 4th cubed. We wouldn't leave it that way, but what I want you guys to see is that when we are raising a product to the power, 2x to the 4th is a product, right? It's 2 times x to the 4th. This is actually another rule. When we're raising that product to a power, we raise each part of that product to the power. So I need to raise 2 to the 3rd power, and I need to raise x to the 4th to the 3rd power. Right? Remember, 2 to the 3rd would be 2 times 2 times 2. So I would get, for my final answer, 8. And then for x to the 4th cubed, we've already written it out the long way. X to the 4th times x to the 4th times x to the 4th. We know when we're multiplying the same base, we keep our base the same. We add our exponents. 4 plus 4 plus 4 is 12. So we would write our final answer as 8x to the 12th. So in class, we talked about the pattern that we saw between the problem we started with and the answer we ended up with. And we noticed that the exponents on those variables were being multiplied. So when we're raising a power to a power, we multiply the exponents. And then something important to remember, like on C, that coefficient, that 2, actually got raised to the 3rd power in this case. So the coefficient is raised to the power, like 2 cubed. So 2 is raised to the 3rd power to give us the 8. So when we have a power like x to the a and we're raising it to a power, we're going to multiply those exponents. And then also when we have more than one factor in that product, each piece, each factor gets raised to the power. So in this case, we would have x raised to the power ab, and we would also have to raise y to that power as well. So then what does that really look like? So for example 1, we had 2x to the 5th, y cubed, z to the 9th. All of that's being raised to the 3rd power. So we could rewrite that. Just like we said, every piece of the product gets raised to the power. So 2 is going to be raised to the third power. X to the fifth is going to be raised to the third power. Y cubed is going to be raised to the third power. And z to the ninth is going to be raised to the third power. And then we're simplifying. 2 cubed, again, is 2 times 2 times 2, which would give us 8. And then we're raising a power to a power, so the base stays the same. And we're multiplying those exponents, because if we were going to write it out the long way, in this case, I would have to do x to the fifth times x to the fifth times x to the fifth. So I would have 3 sets of those x's. If I were writing it out the long way, that would give me 15 x's that I would have to multiply together. From our y's, keep our base the same. We're multiplying those exponents. Same thing with the z's. So our final answer would be 8x to the 15th, y to the 9th, z to the 27th. Take a moment, pause the video, work example 2. So hopefully when you were working this, you remembered we need to raise every factor of that product to the second power. So 5 gets raised to the second power. X to the 12th is going to get raised to the second power. Y to the 13th gets raised to the second, and z to the 15th gets raised to the second. And then when we're simplifying, remember 5 squared means 5 times 5. So 5 squared is 25. So we're actually raising that coefficient to the power. And then for the rest of it, remember when we're raising a power to a power, our base stays the same, and we're multiplying the exponents. So 12 times 2 would give me 24. If we were writing it out the long way, we would have to write x to the 12th out, so we would write 12 x's multiplied by themselves times another set of 12. That would give me 24 x's in that string. Same thing with y's. We're going to keep our base the same. Multiply our exponents. 13 times 2 is 26. And same thing with our z's. So we get 25, x to the 24th, y to the 26th, z to the 30th. And for rule 4, we looked at problems similar to last class. Right? So if I have 4 squared divided by 4 squared. Last class we talked about dividing the same base. If we were dividing the same base, we would keep our base the same, and we would subtract our exponents. In this case, 2 minus 2 would give us 0. Same thing for h. When we have x to the 4th divided by x to the 4th, we're dividing the same base. We're going to keep our base the same. We're going to subtract our exponents. 4 minus 4 is 0. So we end up with these two bases with a 0 power. When we're looking at exponents, if there's something that has a 0 power, we need to simplify it. So one of your rules talks about what it means to be raised to the 0 power. So we're going to look at these two problems in a different way. So if I were to take 4 squared over 4 squared, and we were going to write it out the long way, right? 4 times 4 over 4 times 4. Maybe somebody thinks about it like we did last class. 4 divided by 4 is 1. 4 divided by 4 is 1. 4 divided by 4 is 1. So in my numerator, I have 1 times 1, which is 1. My denominator, 1 times 1, which is 1. And 1 over 1 is 1. Maybe somebody else, when they saw 4 squared over 4 squared, they thought, oh, well, 4 squared is 16. So we get 16 over 16. But 16 divided by 16 is 1. Somebody else might have thought, well, from the beginning, we're taking 4 squared and we're dividing it by itself. Anything divided by itself is 1, right? 4 squared would go into itself 1 time. So maybe someone thought about it like that and thought, oh, well, then it's going to be 1. Likewise, for h, if we were to write h out the long way, x to the 4th over x to the 4th, then we can go back to that division from last class. X divided by x is 1, 1, 1, 1. So in our numerator, 1 times 1 times 1 times 1 is 1. Denominator, we would also get 1. And 1 divided by 1 is 1. So notice when we were looking at it as dividing the same base, we got 0 for both of those exponents. But when we simplified, regardless of which way we simplified, each time we got 1. So the important thing here, anything raised to the 0 power is 1, but there is an exception to that anything but 0. 0 raised to the 0 power is not defined in our number system. If we had 5 million and we raised it to the 0 power, it's just going to be equal to 1. So x to the 0 power is 1. So as we're simplifying with our exponents, whatever is being raised to the 0 power, we can simplify that to be 1. And then for rule 5, we're actually going to think about rule 5 in connection to last class. So when we were dividing the same base, we said we needed to subtract our exponents. We also thought about if it should be in the numerator or the denominator. Today, I want us to just focus on, well, what if we put it in the numerator? So we did problems E, F, G, and H last class. We're going to focus on those just a little bit. So if I were going to just put x in the numerator, then when I subtract my exponents, I would have to do 4 minus 8, right? It would have to be the exponent of the numerator minus the exponent from the denominator. And when I simplify that, I would get x to the negative 4th. For f, if I were going to put x in the numerator, then I would need to do 3 minus 5, since 3 is the exponent in the numerator, and I would get x to the negative 2nd. For g, if I were going to put x in the numerator, then we would have x raised to the power of 3 minus 4, which is x to the negative 1. And for h, we would have x raised to the power of 2 minus 6, and 2 minus 6 is x to the negative 4th. So we see, if we were going to put x in the numerator, for all of these, we would end up with a negative exponent. However, in exponent land, this is an important piece, you should write this down. We can't have a negative exponent in a simplified answer. So if the instructions say simplify, then your final answer should not have any 0 powers, and there should be no negative exponent for that problem. So then we consider, okay, well, this x to the negative 4th is really equal to 1 over x to the 4th. X to the negative 2nd is equal to 1 over x to the 2nd. X to the power of negative 1 is 1 over x, and x to the negative 4 is equal to 1 over x to the 4th. So in class, we thought about what that connection was. And someone mentioned the reciprocal. Remember, in fraction land, the reciprocal, you're flipping that numerator in the denominator. The reciprocal makes the exponent positive. So if we were to rewrite that number as the reciprocal, then the negative exponent becomes positive. Another way to think about that, the negative exponent lets us know that it's in the wrong part of the fraction. If there is a negative exponent in the numerator, then we would need to move it to the denominator to make the exponent positive. If there is a negative exponent in the denominator, then we need to move it to the numerator to make that exponent positive. When I say we need to move it, I mean that base and the exponent, right? And moving it to the other part of the fraction is finding the reciprocal. It's the same thing. So when we look at number 5, these problems, well, A is really the same thing as problem F from last time. X to the negative 2nd, we would rewrite that as 1 over x to the 2nd for our final answer. B, that x to the negative 1, is actually like G from last class. We would write that as 1 over x to the 1st. So when we move it to the denominator, right, we could think about those as fractions. X to the negative 2nd was in the numerator. When we moved x to the negative 2nd to the denominator, that negative 2 became positive 2 for our exponents. Same thing with B. X to the negative 1 is in the numerator. So there's a negative exponent in the numerator. We move it to the denominator, it makes the exponent positive. Remember, one note, we don't actually need to write an exponent of 1, right? When there's no exponent there, it's understood to be an invisible 1. So C and D are a little different. So let's take a minute and look at those. C says 2x to the negative 3rd. We can think about that as a fraction, so we can put it over 1. But you have to be really careful with this one. That -3 only belongs to the x. And we know that because if that was the exponent of the 2 and the x, we would have to see parentheses. So the only thing with a negative exponent is the x. The 2 does not have a negative exponent. In fact, there's an invisible 1 as its exponent. So 2 does not have a negative exponent. It stays where it is. The only thing with a negative exponent is that x to the -3rd. So we could think about the reciprocal. There's a negative exponent in the numerator, so we need to move it to the denominator. So we're going to move the x to the denominator. That is finding the reciprocal. And when we do that, the exponent, that negative exponent, becomes positive. So our final answer is 2 over x cubed. And then for D, we have 1 over x to the -3rd. So our 1 is fine where it is. It's going to stay in the numerator. But this x to the -3rd, we have a negative exponent. We need the reciprocal. The reciprocal would move it to the numerator. Right? If we have a negative exponent in the denominator, it's telling us it's in the wrong place. We move it to the numerator, and when we move it to the numerator, the exponent becomes positive. Right? We would have a 1 in the denominator. We don't need the 1 in the denominator, and we also don't need to write the 1 as the coefficient of x cubed, so we could just write x cubed. So x to the power of -a, we would write as 1 over x to the a. The reciprocal makes that exponent positive. That's it for Rule 4 and 5. The notes are on Power Learning if you need them. Thanks.